I wanted to review reversible versus irreversible processes. Let's consider that we have a system in state 1 and our surroundings are in state A. If we do some process and we change our system into state 2 and our surroundings are now in state B, if this path is reversible, if it's done reversibly, that means if it's done so slowly that the system and surroundings are always in equilibrium, then we can return along a reversible path and we can restore simultaneously our system to state 1 and our surroundings to state A. Now let's consider an irreversible process. If we take our system in state 1 and the surroundings are in state A and we do some irreversible process that gets our system to state 2 and our surroundings to state B, if this is done irreversibly, then we can't go back to state 1 and state A simultaneously. We can, however, restore our system to its starting state, so we could get to state 1 through some pathway, but the surroundings would be in some other state than we started, so state C. Or we could get back to state A of the surroundings, but our system would be in some new state. So for an irreversible process, we can't simultaneously get our system and the surroundings back to their starting state. Let's look at why. In an irreversible case, this is any time that we have a spontaneous process. For a spontaneous process, the change in entropy of the universe is greater than 0. We can imagine that if going from state 1 to state 2 involves an increase in the entropy of the universe, so it's a spontaneous process, then going from state 2 back to state 1 would need to involve a decrease in entropy of the universe. This would be a violation of the second law of thermodynamics. It couldn't happen. So for an irreversible process, we can never go back to our exact starting place. We could restore the system or we could restore the surroundings to their starting place, but we couldn't simultaneously restore them both. And this is because to restore them both would involve decreasing the entropy of the universe. So how come we can do it for a reversible case? Well, in a reversible case, we've got everything always at equilibrium. When we're at equilibrium, the change in entropy of the universe is 0. So if it's 0 on the path on the way down, and we take a reversible path on the way back, then the change in the entropy of the universe is 0. So this isn't a violation of the second law if we're always at equilibrium. We can get exactly back to our starting state. Now let's look at irreversible versus reversible compression and expansion in a piston. So I'm going to start with the irreversible case. So imagine that we have some system and it's at pressure 1 and volume 1, and we have some external pressure pushing down on our piston. If we imagine that in this instant P1 is bigger than P external, then this system is not at equilibrium. The piston is going to push up until the pressure inside the system pushing up on the system is equal to the pressure outside of the system pressing down on the piston. So it's going to expand spontaneously until we have P2 V2, where P2 is equal to the external pressure. This is a spontaneous process and it involves a change in entropy of the universe that is greater than 0. If we were to plot the work done in this process, we'd plot pressure versus volume, and we have starting pressure that's high, an ending pressure that's low, P2, a starting volume that's small, V1, and an ending volume that's big, V2. Because this is an expansion, what we're worried about is the opposing pressure. In this case, the opposing pressure is the P external. It's a constant opposing pressure pushing down on the piston. So if it's a constant pressure, then we start at V1, which is here, and our opposing pressure is P external, which we know is equal to P2. So we start at V1 pushing against P2, and we push against that constant pressure, the P external, until we get to V2. The area under this curve represents the work. Since our system is expanding, that means it's losing energy, so the work is equal to the negative area under the PV curve. So we'll call this area A. So this is negative area A. If we say this is an isothermal process of an ideal gas, then we have that delta T equals 0, and so the change in energy of the system is also 0 because it's an ideal gas. And then delta E is always equal to Q plus W, which in this case is 0, and so heat is equal to the negative work. So in this case, we have that the heat flow into the system is equal to the negative work, which means it's positive area A. It's positive, which means heat is flowing in. So we have a heat flow in of area A. Now let's consider the reversible expansion. In the reversible expansion, we need to have the pressure inside and outside the system the same at all times. So if this is P1, V1, and if we have P external, we also need to add some weight to the piston so that the external pressure plus the pressure due to this weight is equal to P1. So let's add, as an estimation, a pile of sand onto our piston. So we have that P1 is equal to the external pressure plus the pressure due to the weight of the sand. If we remove 1 grain of sand at a time, as that 1 grain of sand disappears, then the pressure opposing the piston will decrease. So as P sand, so as the mass of sand goes down, P sand will decrease. The volume will increase a little. This piston will move up slightly, and P1 will go down slightly, so that the pressure inside the system is always equal to the sum of the pressure from the external atmosphere plus the pressure due to the weight of the sand. So if we remove the sand 1 grain at a time, we will slowly raise our piston, but everything's always in equilibrium until we get to the same ending point where P2, V2, and we have P external. We've removed our last grain of sand, so that very last little lift of the piston is just against the external pressure. So in this case, at the beginning, the pressure we're lifting against, the opposing pressure, is P external plus the pressure due to all the sand, and that's equal to P1. So we start at V1, P1 for the reversible case, where everything's been in equilibrium. And we end at the exact same place we ended at before, which is P2, V2. Now, as we decrease the pressure infinitesimally slowly, we find that this would follow this curve here. So this is an isothermal expansion. So again, just like before, the heat is equal to the negative work because we're still working with an isothermal expansion. So if this is the area under our curve here, the signs are going to be the same as for the irreversible case. So the work is going to be equal to negative area B. We'll call this area B. And the heat is going to be equal to positive area B. So the system is doing work on the surroundings, and heat is flowing into the system. So the system spends energy to expand, and that energy is replaced by heat flowing into the system to keep the temperature constant. We can see that the area of B is larger than the area of A, which means that the system in the reversible case has done more work than the system in the irreversible case. This makes sense because the system in the reversible case had to lift at the beginning the external pressure plus all the pressure due to that sand, rather than in the irreversible case where it was only having to lift against the external pressure.